I want you to just picture a scene for a second. You are standing right in the middle of this ancient, incredibly muddy forest.
Oh, yeah, set the scene.
Right, so it's twilight. The air is thick, it's misty, and you hear this heavy, rhythmic snapping of twigs, crunching leaves.
But you know it's not an animal.
Exactly. It's not a deer, it's not a bear. Stepping right out of the fog is this dark, sleek, robotic horse.
Which is just an incredible mental image.
It really is. And it's trotting effortlessly through this deep, thick mud. Completely autonomous. And as it turns toward you, the mane, which is made entirely of these integrated LEDs, it glows softly in red, white, and blue, the colors of the Croatian flag.
It's like something straight out of cyberpunk, but dropped into a traditional village.
Yeah, exactly. It is simultaneously this vision from a high-tech future, but also a deeply rooted echo of the rural past.
Well, the engineering concepts are very real.
Right. This is the Croatian Rural Assistant, and we're doing a deep dive today into a stack of sources, a primary concept document by Luka Jagor, and a deeply technical engineering breakdown. And our mission today is to figure out why this machine is here, to prove that Silicon Valley's absolute obsession with human-shaped robots might just be completely wrong.
Yeah, and what's fascinating here is that it completely arrests your attention. You know, it forces two entirely disparate frameworks into the same exact physical space.
Mud and microchips.
Mud and microchips, exactly. You've got hyper-advanced autonomous engineering colliding with traditional messy agriculture. And the documents we're looking at today, it is a rigorous, heavily stress-tested challenge to the entire trajectory of modern robotics. We're looking at a fundamental argument about form, function, and really philosophy. We're asking why a machine designed for the wild, for nature, must be fundamentally different from a machine designed for a flat factory floor.
Okay, let's unpack this. Because if we are going to challenge giants like, Tesla and Boston Dynamics, we really need to understand the physical reality of this machine first.
Yeah, the nuts and bolts of it.
Right, and the specs outlined in the source material are super aggressive. It stands 1.6 meters tall at the shoulders.
So pretty sizable, about the size of a real smaller draft horse.
Yeah, exactly. And it's built entirely from lightweight carbon fiber and titanium. Visually, they specifically designed it with this matte, dark brown or black finish.
Which I love, because the reasoning isn't aesthetic at all.
No, it's totally operational. It's designed specifically to hide mud, hide dust, and just blend into the inevitable wear and tear of a brutal environment.
You don't want a pristine white robot in a swamp.
Right. I mean, think of those sleek white robots you see in viral videos. They look terrible after 5 minutes in a Slavonian forest. Anyway, it has this broad chest, a really low center of gravity, and the legs are engineered to carry a massive 250-kilogram payload.
Which is really where the material science becomes the immediate bottleneck for the engineers.
Oh, for sure. Carrying 1/4 of a ton is no joke.
You mentioned titanium and carbon fiber, and the rationale there goes way beyond just basic strength. Titanium is utilized because of its exceptional corrosion resistance.
Because it's dealing with water all the time.
Water, yeah, but also agricultural chemicals, heavy fertilizers, constant moisture from the underbrush. All while maintaining a tensile strength that can actually handle the sheer mechanical shock of a 250-kilogram load dropping off a sudden ledge.
Like stepping off a rock hidden in the mud.
Exactly. And the carbon fiber is deployed for the chassis mainly to offset the immense weight of the power systems. In legged robotics, weight isn't just a physical hurdle, it's a computational one.
Wait, how is weight computational?
So every single gram you add to the chassis exponentially increases the torque required by the actuators in the joints.
Oh, I see.
Right. And more torque means it draws more current from the battery, which generates more heat, which requires more cooling systems, which adds more weight.
Ah, right. The vicious cycle of robotics.
Exactly. So the carbon fiber is absolutely essential to keep that baseline weight as low as possible.
Okay, so speaking of drawing current, to supply all that power, it relies on a high-density lithium-ion system. But the concept pairs that with solar panels physically integrated right into the back of the chassis.
Yeah, on the upper casing.
And the claim in the sources is 15 hours of operation. I have to admit, when I first read that, my immediate thought was total skepticism.
Oh, yeah, it sounds a bit optimistic.
Right. I mean, solar panels on a muddy, moving object operating under a dense forest canopy. Like, how much wattage are they actually pulling from that?
Well, it's less about primary propulsion and more about parasitic drain mitigation.
Okay, break that down for me. Parasitic drain.
So the solar array isn't meant to power the dynamic locomotion. Making a heavy robot walk requires thousands of watts of immediate output. A small solar panel can't do that.
It's not a solar-powered car.
Right. Instead, the solar integration handles the persistent low voltage draw of the sensor suites. Things like the edge AI processors, the LiDAR spin, the communication modules.
Also the brain and the eyes.
Yes, because those things are always on, always drawing a little bit of power. By offloading that constant computing power draw to the solar array, the lithium-ion reserves could be dedicated almost entirely to the motor controllers for actual movement.
That is incredibly smart. It's like a localized energy triage system.
Exactly. And the physical connection to the ground is equally specialized. The sources talk about these smart horseshoes.
Right, yeah. The smart horseshoes with adaptive grip.
They utilize this variable geometry to mechanically lock into deep mud or, flatten out for slick rock.
So the hardware is just heavily optimized for a totally chaotic environment. But honestly, the software is where this gets highly specific and really fascinating.
The AI architecture, right?
Yeah. It takes direct inspiration from Japanese innovations, specifically platforms like Sony's Aibo.
The little robot dog?
Exactly. It utilizes TensorFlow for observational learning. But the sources are very explicit about this one thing. They completely stripped out the companion pet simulation.
Right. This isn't designed to be cute or play fetch.
No, not at all. It uses observational reinforcement learning purely to adapt its kinematics. It learns, practically speaking, how the thick mud in Slavonia shifts differently than the loose, rocky soil down in Dalmatia.
And that distinction is really critical. Observational learning in this context means gait optimization.
Gait, as in how it walks.
Yes. When the robot walks across an unstable surface, those force sensors in the smart horseshoes feed resistance data directly back into the neural network.
So it feels the ground.
It does. If it slips on a wet limestone slab, the AI instantly updates its local terrain model. It alters the strike angle and the torque delivery for the very next step, and the thousands of steps after that.
So it doesn't just stumble blindly, it's learning the physics of its specific environment in real time.
Exactly. It's mapping the friction coefficients of the forest floor continuously.
But, the paradox here is that while they stripped out that pet aspect, they injected a massive amount of localized personality into this thing.
Oh, the cultural flair. It's amazing.
It really is. The cultural user interface, the UI on this machine, is practically a masterclass in behavioral psychology. I mentioned the LED main earlier.
The red, white, and blue one.
Yeah. But it's not just patriotic lighting. It serves as an actual visual telemetry display.
Like a dashboard.
Right. So it glows red when it's actively towing heavy machinery. It turns blue during environmental scanning or data processing. And it shines bright white when it's just acting as a localized work light for a farmer at night.
Which is brilliant because it creates an intuitive communication protocol that requires absolutely zero technical literacy from the end user.
Yes. You don't need a manual.
Right. An 80-year-old farmer doesn't need to pull out a smartphone and check a 5G dashboard app to know what state the robot is in. They literally just look at the color of the mane.
Exactly. And wait, it goes beyond even just the lights. The acoustic UI is incredible.
The voice assistant.
Yes. It features a voice assistant with a highly specific Croatian accent. And it utilizes regional dialects, too.
Which is such a nice touch.
It is. It says things like, "Good morning, boss," or "Let's go to work." And this is the part that blew my mind. It has localized audio drivers that can literally flatter the mane to the rhythm of a tambourine.
While playing local music, right?
Yeah. It can play Slavonian folk hits like "Slavonia, I Love You" right out of its speakers while it's autonomously plowing a field. At first, I read that and thought, okay, this has to just be a gimmick.
It sounds like a party trick.
Right. But it's not, is it?
Far from it. It's a highly calculated deployment of cultural resonance.
To get people to actually use it.
Exactly. It's about overcoming the adoption barrier of advanced automation. Remember, we are talking about deeply traditional, often depopulating rural areas.
Where people might be naturally skeptical of high tech.
Highly skeptical.
Yeah.
If you parachute a sterile, silent, white plastic Boston Dynamics style machine into a rural village in Rijeka, it evokes apprehension.
It feels a little dystopian, like a robot takeover.
Exactly. It feels alien. But by wrapping hyper-advanced edge AI and titanium actuators in the familiar phonetic and visual language of that specific region, the machine transitions from a foreign tech imposition to a local village helper. That's a great way to put it. It leverages folklore to domesticate the technology.
Yeah.
So it's not a cold appliance. It's a companion that participates in the spirit of the countryside.
Okay, so that perfectly bridges into the next part of our deep dive. How does this domesticated technology actually operate when it hits the mud? What are the practical use cases?
Because all these cultural features have to be tied to actual labor.
Right. And the source outlines some absolutely grueling daily scenarios across regions like Slavonia, Lika, or Dalmatia.
The real heavy lifting. Yeah.
Literally. Pulling heavy plows, towing agricultural machinery that gets stuck, carrying massive loads of wet firewood out of dense, uneven brush where a tractor can't fit.
And beyond just brute force, it acts as an autonomous logistics bridge.
Because of the aging population.
Exactly. The demographic reality of these rural regions is extreme depopulation and aging. The younger generations move to the cities. So the robot is tasked with autonomous grocery and medical delivery to isolated elderly residents who can't make it into town.
Wow, so it's a lifeline.
It is. And during periods of infrastructural collapse like post-earthquake scenarios or severe flood events, which happen, it transitions into an emergency courier. It can navigate fractured terrain, washed out dirt roads, and debris fields that wheeled or tracked vehicles simply cannot negotiate.
And while it's running all these logistics and hauling wood, it's also quietly operating as a mobile environmental lab.
The sensor suite is doing double duty.
Exactly. The LiDAR and cameras aren't just for navigation. The sources detail how it analyzes soil fertility and humidity as it walks. It checks water quality when it wades through flood zones and monitors airborne particulates.
Constantly gathering data.
Right. It aggregates all this microclimate data and beams it via an onboard 5G module back to a centralized agricultural network.
Yeah.
So every single hauling trip actually becomes a high-fidelity data gathering mission for the whole region.
It's brilliant. But out of all the operational use cases mentioned in the documents, the application for the Alka of Sinj is by far the most mechanically demanding.
And culturally profound, I'd argue.
Oh, absolutely.
Yeah.
The Alka of Sinj represents a massive stress test for this robotic platform.
For our listeners who might not know, give us a quick breakdown of what the Alka actually is.
Sure. So it's a UNESCO-protected traditional nightly game. It's a huge deal. It requires a rider who is called an Alkar to gallop on horseback at full speed and drive a long lance through a tiny suspended metal ring.
It requires incredible precision and speed.
Yes. And historically, organizing this event globally, like trying to hold an exhibition in another country or even a distant city, has been an ethical and logistical nightmare.
Because you have to move the horses.
Right. You're transporting highly trained biological workhorses across borders, managing their physiological stress, the quarantine periods, maintaining perfect veterinary conditions. It's incredibly taxing on the animals.
So the proposal in the source is to use this robotic horse as the platform for expanding the Alka internationally. You could hold it in Zagreb or Split or even abroad, but honestly, the physics of that are terrifying to me.
Oh, it's an engineering nightmare.
Because the robot has to hit galloping speeds of 40 kilometers per hour. And it's not just carrying dead weight like a sack of potatoes.
No, it's carrying the dynamic, shifting human rider.
Right. A human rider holding a long metal lance.
Yeah.
How on earth does a machine manage the kinematics of the humans throwing their weight around at 40 kilometers per hour without just catastrophically failing and rolling over?
That requires an entirely different tier of active suspension and inverse kinematics.
Explain inverse kinematics, because that sounds intense.
Well, think about it like this. When the human rider leans to one side to aim the lance, they shift the center of mass dramatically off axis.
So the robot should tip over.
Exactly. But the robot's onboard processors predict that shift in real time. It instantaneously adjusts the compliance or the stiffness in the contralateral legs, the legs on the opposite side, to prevent a rollover.
So it pushes back against the rider's lean.
Yes. The spring damper systems in the legs must absorb not only the impact of the 40 kilometer per hour gallop, but also the localized kinetic shock when that lance actually strikes the metal target.
Oh, wow. Yeah, that impact force travels right down the rider's arm and into the saddle.
Right into the robot's chassis. So it requires processing microsecond adjustments to the joints so the human rider experiences a perfectly stabilized platform.
And it does all this while maintaining the authentic atmosphere. The main lights up, the onboard audio drivers pump out Dalmatian Klapa songs.
So it preserves the sensory experience of the event.
While totally isolating the human skill element, the aim of the Alkar, and just upgrading the underlying hardware. And, this ties directly into the ethical partnerships that are outlined in the text.
Right, the collaboration with animal rights groups.
Yeah. The concept integrates with a group called Animal Friends to advocate for the removal of biological horses from high-stress labor and these extreme transport scenarios.
It frames advanced robotics not as a replacement for nature, but as an active tool for animal liberation.
Which is a very cool way to look at it.
It is. By deploying machines that are capable of handling the extreme kinetic and thermal demands of hauling and competitive sprinting, biological horses are just removed from the industrial and entertainment supply chain entirely.
And they aren't just partnering with animal rights groups, they are also looking at the next generation of engineers. The source details a proposed collaboration with CircuitMass.
Oh, the Croatian STEM startup.
Yeah, founded by Albert Gajak. This is the same guy who previously pulled in nearly $390,000 on Kickstarter for an AI Batmobile kit.
Which is wildly successful.
Right. And the strategy here is to turn the robotic horse's architecture into a modular educational platform. They're essentially proposing open sourcing aspects of its AI and robotics to teach students how to build these systems.
It's an incredible educational tool.
It is. But here's where I really have to push back on the entire premise. I have to play devil's advocate.
Please do.
I'm looking at the sheer mind-boggling complexity of a four-legged, 40-kilometer-per-hour, 250-kilogram hauling robot. And I keep coming back to the exact same question. If the goal is purely utilitarian like hauling wood or taking sensors into a flood zone, why make it look like a horse at all?
Why not a vehicle?
Right. Why not just engineer an incredibly robust, low-profile, autonomous, remote-controlled tractor? Or a tank tread vehicle? Tracks distribute weight beautifully over mud.
That is the exact debate happening at the highest levels of modern robotics right now.
Because it just seems so much simpler to use wheels or tracks.
You'd think tracks are the ultimate off-road solution. But that assumes the terrain is continuous.
Continuous, meaning flat.
Meaning unbroken. Tracks and wheels are fundamentally dependent on a continuous path of contact. They are instantly defeated by vertical discontinuities.
Like a wall.
Or a massive fallen log, a sheer rock step, or the deep, unpredictable trenches of an abandoned vineyard. A tracked vehicle has to drive over or through an obstacle.
Which takes a lot of power.
Immense energy. And it causes immense environmental destruction, tearing up the soil. But a quadrupedal-legged robot can simply step over the discontinuity.
Oh, right.
It requires only 4 isolated points of contact at any given time, meaning 90% of the ground beneath the chassis can be entirely unnavigable, just a gaping hole, and the robot can still traverse it by picking its footholds.
Okay, that makes perfect sense for a forest. But that brings us to the core philosophical war in the industry. If we accept that wheels and tracks are too limited in the wild, why not build a human shape?
The bipedal approach.
Yeah. The source material specifically contrasts this horse project with industry darlings like Tesla Optimus and Boston Dynamics Atlas.
The prevailing dogma in Silicon Valley is that the world is built for the human form factor.
Right. They argue that factories, homes, stairs, door handles, hand tools, they were all made for us. Therefore, our generalized autonomous labor should look like us, bipedal.
And that dogma is completely valid. If your operational environment is an Amazon fulfillment center or a residential kitchen.
Sure.
But the thesis of the Croatian rural assistant is that the rural terrain is optimized for animals, not for sidewalks. The bipedal form factor is, from a physics standpoint, an incredibly unstable, highly inefficient inverted pendulum.
Right. I mean, humans constantly fall over in the woods.
We do. We trip on roots all the time. When a biped walks on a steep, muddy incline, it is constantly fighting gravity just to maintain verticality. You're constantly calculating the exact moment of free fall with every step.
So the energy expenditure just to not fall over is huge.
Astronomical. Furthermore, a biped has a very high center of gravity. So if it slips, the recovery time and the sheer kinetic impact of the fall are massive. You have a lot further to fall.
Whereas a quadruped, a horse, drops the center of mass down to a fraction of that height.
Exactly. It has inherent static stability. You can literally turn the power off on a four-legged robot, and the structure remains standing.
Oh, wow.
You turn the power off on a bipedal robot, and it just crashes to the floor instantly.
That is a brilliant point. And the horse platform also bypasses the need for highly complex, super fragile human hands through what the sources call modularity.
Modularity is really the economic counterargument to the generalized humanoid.
Because making a robot hand that can pick a strawberry and hold a hammer is incredibly expensive.
And delicate. Humanoids attempt to use these hyper-articulated fingers to operate tools that humans use. The horse concept abandons the tool operator paradigm entirely.
Well, horse doesn't hold the tool.
The horse is the tool platform.
Right. So instead of a robot trying to hold a heavy sprayer with metal fingers, you just swap out the cargo saddle for a dedicated agricultural sprayer module.
Or a drone docking station. Or a medical support kit. You integrate the tool directly into the power matrix of the chassis.
So what does this all mean? If we synthesize this, it means trying to fight Tesla, Alphabet, or Figure AI in the generalized humanoid space is just a massive fool's errand.
Oh, absolutely. They possess infinite compute, infinite capital, and vertical integration in manufacturing. You can't beat them at making a factory worker.
Right. But dominating the hyper-specific niche of rugged, autonomous, high-payload rural mobility, that is a highly defensible strategy.
You bypass the absolute bloodbath of the factory floor robotics market, and you establish a total monopoly in the forest.
That is strategic brilliance. However, isolating a defensible niche does not negate the sheer physical impossibility of the engineering required to pull this off.
No, the physics don't care about your market strategy.
Right. The environmental and physical variables in a chaotic forest are exponentially higher than on a flat, climate-controlled factory floor, and the engineering breakdown in our sources lists these technical hurdles, and they are uncompromising.
So let's get into the brutal reality of the hardware, because building this is a nightmare.
Let's do it. The hardest challenge listed is dynamic locomotion under shifting payload. We discussed that 250 kilogram capacity earlier.
Right, the quarter-ton payload.
So when this massive titanium frame steps onto a muddy 30-degree incline, and the loose rocks beneath the surface suddenly give way, how does it not just snap its own joints backward? I mean, bipedal robots struggle with a fraction of that dynamic shock.
They do, because standard rigid robotics fail under those parameters.
Rigid robotics.
Yeah, so if you rigidly bolt a high-torque actuator, a motor, directly to a solid titanium leg, the kinetic shock of that 250 kilogram load slipping and then suddenly catching traction will strip the gearing or shatter the housing instantly.
The metal literally just breaks.
Exactly. Biological horses solve this with tendons. Tendons act as natural springs to store and release kinetic energy while providing a buffer against that immense shock.
So how do you build a robotic tendon?
The robotic equivalent requires highly advanced compliant mechanics.
Meaning the mechanical structure has to have physical give.
Precisely. It requires what are called series elastic actuators.
Okay, series elastic actuators, how does that work?
Instead of the motor driving the joint directly, it drives a highly calibrated spring mechanism, and then that spring mechanism drives the joint.
Oh, so there's a shock absorber built into every movement?
Yes. This introduces a mechanical low-pass filter against kinetic shock. So if the foot slips, the spring takes the hit, not the motor gears. Furthermore, it requires instantaneous inverse kinematics, like we talked about with the rider.
But applied to just walking.
Right. When the foot selects, the force sensors detect a microsecond drop in resistance. The edge processor must immediately recalculate the necessary joint angles for the hip, the knee, and the ankle to reposition that foot,
while not falling over,
while simultaneously adjusting the torque on the other three legs to maintain the overall center of mass, and all of this has to happen in milliseconds.
In driving those joints requires immense raw power. The sources mention the need for high-torque electric servo actuators paired with cycloidal gearboxes.
Yes, cycloidal gearboxes are crucial here.
So why cycloidal? Why not standard planetary gears? We hear about planetary gears in robotics all the time.
Planetary gears utilize toothed interlocks. They literally have metal teeth that lock together. Under the extreme sudden shock loads of a falling 250 kilogram chassis, those teeth will just shear right off. They'll be stripped bare.
Oh, yikes. So what makes cycloidal different?
Cycloidal gearboxes utilize a lobed disc moving eccentrically within a ring of pins.
Okay, that sounds complicated.
It is, but the simple version is this. Because the force is distributed across a massive surface area of multiple pins simultaneously, rather than just a few delicate teeth, they can handle extraordinary shock loads.
They spread the impact out.
Exactly. And they deliver immense torque with near zero backlash.
But those high-torque motors introduce the most notorious trap in all of robotics, what the source has called the vicious cycle of weight. Okay, if you want to carry 250 kilograms of wet timber, you need incredibly strong motors, right? But strong motors draw massive, continuous current. To supply that current without the robot dying in an hour, you need larger, higher-capacity battery packs.
But adding high-capacity lithium-ion packs adds tremendous mass to the chassis. Batteries are heavy.
Extremely heavy. So now, to move that newly added mass efficiently, Your motors now need to be even larger.
And draw even more current.
Completely negating the battery upgrade you just did.
Exactly. You enter this death spiral of diminishing returns where the robot eventually becomes too heavy to even support its own operational parameters.
So how do they get around that? Most real-world quadrupeds currently operating in the field max out at 1 to 3 hours under load?
Yeah, 3 hours is pushing it.
Yet achieving the 15-hour operational time claimed in this concept requires something else, and the document says it relies heavily on regenerative braking.
Which is similar to what electric cars use.
Right. When the robot is walking downhill, the massive weight of the payload actually forces the motors to act as generators.
Yes. It converts the kinetic resistance of walking downhill back into electrical energy to feed the lithium reserves.
But managing all that electrical flow pushing power out, pulling power back in, introduces the invisible killer of autonomous systems: thermal dynamics, heat.
Heat will destroy a robot faster than a sledgehammer.
Seriously. Pushing massive current through sealed actuators while hauling a quarter-ton uphill in the peak of a Croatian summer, it generates catastrophic heat.
And you can't just put a standard spinning computer fan on it.
No, because the system has to be completely hermetically sealed against mud, water, and agricultural dust. If mud gets in a fan, it stops working instantly.
Exactly. So the thermal engineering requires massive passive heat sinks integrated directly into the carbon fiber geometry.
Like metal fins to dissipate the heat.
Right. Or potentially active liquid cooling systems, literally coursing through the chassis like a circulatory system of a biological animal, pulling heat away from the edge eye processors and motor controllers and dissipating it through the outer titanium shell.
Wow. It really is an artificial animal. Speaking of the edge processors, let's talk about the autonomy stack. Because navigating this machine in the wild is terrifyingly complex compared to an urban environment.
Oh, night and day.
A self-driving car, like a Tesla, uses its cameras to read lane lines, traffic lights, street signs. In a dense pine forest, there are no lane lines. There are no stop signs. It's just visual chaos. Every tree looks slightly different. Shadows are moving.
And furthermore, under a thick forest canopy, GPS signals are heavily degraded or entirely non-existent.
Which totally eliminates cloud computing and standard satellite navigation. You can't rely on Google Maps in the middle of a ravine.
No. The robot must achieve true local autonomy. It utilizes SLAM, which stands for simultaneous localization and mapping.
Okay, SLAM. And it does this using LIDAR.
Yes. The LIDAR array blasts lasers into the environment thousands of times a second to generate a high-density 3D point cloud of the area around it. Meanwhile, the stereo cameras provide depth perception and visual classification.
But LiDAR struggles heavily in foliage, doesn't it? Like, a dense, leafy bush looks like a solid brick wall to a laser.
It does. And that is exactly where the edge AI becomes critical. The neural network has to interpret that point cloud locally without any internet access to check a database.
It has to make a judgment call.
Yes. It has to look at the sensor data and classify the geometry. Is that visual artifact a solid boulder that will shatter my leg? Or is it just a soft fern that I can push right through?
Is that dark patch a shallow puddle? Or is it a deep, bottomless mud sinkhole?
Precisely. And it has to do all of this spatial reasoning while simultaneously calculating its own inverse kinematics, balancing a 250-kilogram payload and monitoring its internal thermal limits.
It is essentially a high-powered data center trying to balance on a tightrope over a mud pit while simultaneously solving advanced calculus locally to decide where to place its foot next.
That's a very accurate summary.
But despite all that computational power, eventually, no matter how good the AI is, it is going to fall over.
Gravity always wins eventually.
A wet rock shifts underneath it, the payload imbalances, and 250 kilograms of titanium goes down hard in the dirt.
Which is why fall recovery is a non-negotiable engineering requirement in the source document. The system must possess predictive fall algorithms.
Meaning it knows it's falling before it hits the ground.
Exactly. If the internal gyroscopes detect that the center of mass has passed the point of no return, meaning it cannot be saved, the AI instantly stops trying to balance.
It gives up.
It abandons balance and instantly transitions to damage mitigation. It rapidly reconfigures the limbs midair to shield the most fragile components, like the expensive LiDAR arrays and the camera gimbals, from direct impact. It essentially braces for impact.
Like a person throwing their arms out to protect their face.
Just like that.
And then, once it's lying in the mud, it requires the kinematic geometry to execute a self-righting maneuver. It has to figure out how to untangle its own limbs, find solid purchase in the slip terrain, and lever a quarter-ton back into a standing position on completely uneven ground.
Which is a massive feat of torque and leverage. Because if it lacks the power or the physical geometry to self-right,
it becomes an incredibly expensive piece of modern art just rusting away in a ravine.
Exactly. A total loss.
So the physical and computational engineering required to simply keep this machine alive in the wild is basically aerospace grade.
It is.
But what elevates this entire project from the brilliant mechanical schematic into a radical new philosophy of technology is the final layer of the design framework. Because making it survive the forest is only step one.
Step two is ensuring the forest survives the robot.
Yes. This is where my perspective on this whole deep dive shifted entirely. The source text dives really deep into the philosophy of ecological compatibility.
Which is so rare in heavy robotics.
It really is. In the mainstream robotics and agricultural industry, the core optimization target is always dominant.
Always. It's how much can it lift? How fast can it conquer this terrain? How efficiently can it exert its will over the natural environment?
But this concept flips that paradigm completely upside down. The optimization target becomes behavioral ecology. The fundamental question changes from what can this robot do to how little damage does it inflict while doing it?
It demands that we stop designing robots purely as industrial machines and start designing them as artificial actors within an existing fragile ecosystem.
Right. And the document breaks down the sheer violence that traditional machines inflict on nature. When you drive a standard agricultural tractor through a forest, the localized pressure from those massive tires crushes root systems. It permanently compresses the soil, which destroys vital microhabitats for insects and fungi.
It suffocates the ground.
Yes.
But a quadruped mitigates that physical damage inherently by utilizing biological load distribution.
Explain that, biological load distribution.
So by spreading the 250-kilogram payload across 4 adaptive compliant contact points, the hooves, the pounds per square inch exerted on the soil, drop dramatically compared to a heavy wheel that's constantly grinding forward.
It leaves footprints, not deep trenches.
Exactly. But the physical interaction with the dirt is really only a fraction of the ecological impact. The sources place a massive, unexpected emphasis on an often ignored pollutant.
The acoustic footprint.
Yes. Acoustic pollution.
We generally don't view noise as a toxin in the same way we view exhaust fumes, but in a biological ecosystem, auditory disruption is catastrophic.
It is. A high-pitched electrical whine from a servo actuator, or the grinding of a planetary gear under heavy load that can trigger severe stress responses in local wildlife.
Right. If a gear whines at a specific high frequency, it could mimic a distress call or just blanket the forest in unnatural noise.
Which disrupts feeding patterns, prevents animals from hearing predators, and can even alter entire migration corridors over time. If a forest is too noisy, animals will abandon it.
Therefore, the acoustic signature of this robotic horse is treated with the exact same engineering rigor as its thermal limits. The motors must be heavily damped for low-frequency output.
The cycloidal gearboxes must be fully acoustically insulated within the carbon fiber chassis.
So it's essentially operating stealthily, but not for military reasons. Operating silently isn't a stealth requirement. It is a fundamental biological necessity for coexistence.
It's about being a polite neighbor in the woods.
Exactly. But the absolute most staggering conceptual leap in this entire deep dive, the thing that really made me pause, is a software framework the source refers to as the path respect system.
So this is brilliant. It is a total reinvention of traditional pathfinding logic.
Because standard robotic AI utilizes algorithms like A or Dijkstra's algorithm to find the absolute shortest, most energy-efficient route between point A and point B, right?
Right. Standard algorithms view the environment purely as a geometric obstacle course. It calculates the math, and it does not care if it crushes virgin flora or plows through a delicate moss bed just to save 3 seconds of transit time.
It's ruthless efficiency.
Very ruthless.
Mm-hmm.
But the path respect system modifies the actual cost function of the navigation algorithm to include a variable for ecological disturbance.
Wow. So it calculates the cost to nature.
Exactly. The AI is trained to utilize its stereo cameras and LiDAR to identify existing human footpaths, natural animal trails, and highly sensitive erosion zones. It actively prefers to route itself over terrain that has already been disturbed.
So it will intentionally choose a longer, more computationally difficult, more energy-intensive route just to preserve virgin soil.
Yes. And it adapts dynamically, too. If the sensors detect that a familiar trail is dangerously muddy due to recent spring rains, The algorithm recognizes that traversing it today would create deep, permanent ruts.
So it won't just blindly follow the path and ruin it.
No, it will recalculate to find firmer ground nearby, willingly sacrificing its own battery efficiency for long-term ecological preservation.
That is mind-blowing. It operates under a directive the source specifically defines as soft interaction with living systems.
Soft interaction, I love that term.
Standard collision avoidance in a factory robot is rudimentary. If an object enters the path, the robot abruptly stops or an alarm goes off. But the robotic horse utilizes disturbance minimization,
which requires deeply complex behavioral analysis.
Give me an example of how that looks in the wild.
Sure. So if the robot's thermal and visual sensors detect a flock of grazing animals ahead on the trail, say a group of deer, it doesn't just stop rigidly or honk a horn to scare them away. It fundamentally alters its kinetic profile.
It changes how it moves.
Yes. It intentionally slows its gait to reduce sudden threatening movement. It lowers its noise profile even further. It deliberately avoids rapid, jerky exploration loops with its sensor head, because moving its head too quickly might mimic a predator's scanning behavior and trigger a panic response.
So it exhibits a programmed, predictable humility.
Exactly. Humility in motion.
And I just keep coming back to how profoundly counterintuitive that is to our entire history of industrial conditioning. For centuries, our engineering baseline has been to build machines that bend nature to our will, to bulldoze it, to pave it, to overpower it.
We engineered dominance.
Exactly. The idea of spending millions of dollars developing a hyper-advanced titanium and carbon fiber machine running incredibly complex edge AI purely so it can learn how to defer to a deer on a dirt path, I mean, it's a radical abdication of technological arrogance.
It is, but it's also the ultimate realization of efficiency, if you look closely.
How so?
By aligning the machine's operational parameters with the millions of years of evolutionary optimization that biological horses have already achieved. You know, their localized ground pressure, their gait mechanics, their silent energy transfer. The robot doesn't have to spend vast amounts of battery and compute power fighting the ecosystem.
Oh, I see. It doesn't fight the mud. It works with it.
Right. It just slips seamlessly into a localized niche that nature has already prepared for it over millennia.
It leverages biology as the ultimate R&D department.
Beautifully said.
So taking a step back and looking at the entire massive architecture we've explored today, we started with this really striking visual image. A dark robotic horse with a glowing mane playing tambourine music while pulling a plow. A concept that honestly sounded almost absurd at first glance.
A bit whimsical.
Yeah. But when rigorously analyzed, when we dive into the sources, it reveals itself as an incredibly serious, highly defensible blueprint for an autonomous electric mule.
It bypasses the crowded, hyper-competitive market of generalized humanoids. It doesn't want to be a factory worker. It wants to dominate the exceptionally brutal, entirely unserved niche of rugged, high-payload rural mobility.
It solves the physical realities of the mud. It addresses the demographic collapse of rural farming by helping the elderly. And it mitigates the kinetic violence of heavy industry. It respects tradition by carrying the Alka in the nightly games. It educates the next generation through open-source STEM frameworks. And most importantly, it actively minimizes its own existence in the forest through the path respect system.
It really proves that as we push the extreme boundaries of artificial intelligence and material science, our machines absolutely do not have to become cold, generic human replacements. They can be culturally resonant, ecologically integrated actors that reflect the specific, beautiful environments they inhabit.
It's an inspiring vision, and it leaves you with a final implication that fundamentally alters how we might view the future of the wild.
Yes.
If we successfully engineer systems with perfect behavioral restraint, utterly silent actuators, dynamic path respect algorithms, and materials that navigate the woods without leaving a trace.
If we get it totally right.
Right. If we build a machine that perfectly mimics the harmony and humility of a biological organism, at what point does the line between an engineered robot and a completely new digital species completely dissolve? If that quiet, dark, robotic horse steps out of the foggy, muddy forest and slips by you without breaking a single branch, will the forest even know the difference? Something for you to think about next time you walk in the woods. Thank you so much for joining us on this deep dive. Keep questioning, and we'll see you next time.